Okay, my name is Ian Griffiths. I'm the principal consultant here at Grey Matters, and welcome to this guide on earth testing. Okay, moving on, a couple of announcements. We are looking for a talented graduate engineer. So if you graduated recently in either an engineering discipline or physics, mathematics, any of those kind of disciplines, then please, if you are somebody that is that person, drop me a DM again on the chat. That's private, and we'll take it offline. Or if you know somebody that has those, looking for a new opportunity, then again, DM me, and we'll take that offline. Other thing, access to the back catalogue of webinars is going to be completely free, returning to free again. So if anytime in the future you need to refresh on something, you can go back and dip into it as before. So let's get this show on the road. Back to earth testing. Today we're going to talk about basic earth testing, and we're going to answer a couple of questions, a few questions actually. Why do we need to do an earth test in the first place? What's the purpose behind an earth electrode? And back to the fundamentals, how it works, what they look like, that kind of thing. And methods of testing, before we then dive into a little bit more of a deeper dive on full potential test, which is one of the most commonly accepted methods across the world. And finally, the common pitfalls or common mistakes that we're looking to avoid to save us time, hassle, stress, and all the rest of it, and revisits and those kind of nasty stuff. So, earth resistance testing. Why do we do it? Once a new electrode has been designed and installed, we need to verify that it'll perform as we predict it will perform. In the same way, if it's an existing electrode, then we need to know that it's still going to be performing as we originally intended it to. So the most convenient / easiest way to do this is with a performance indicator to measure, and that is earth resistance, the resistance to earth of the electrode itself. Okay, so now before we sort of dive in, let's cover off a couple of the basics. From previous webinars, we know that the purpose of the electrode is primarily twofold. One is to allow the AC electrical equipment to work, so it has a functional purpose. And secondly, is to protect us from the harmful effects of the electricity during a fault or / lightning strike. So those are the two primary functions. One is functional and the other is safety critical. There are sub-purposes, but these are the primary two. So what does an earthing electrode look like? What does an earthing arrangement look like? And there are all sorts of conductive objects and structures. Here, for example, we've got steel structure, significant steel structure. Above ground, this might be to take away the current from a lightning strike, but equally it could be a pile under the ground that can be utilized. Here we've got some foundational electrode where the rebar is connected to another earth grid, buried earth grid mat outside. We've got horizontal electrodes making up a grid, and we've got electrodes that are coated in PVC insulated. There's an interesting one about that, and I'll come on to that in a minute. And rod electrodes. Here we've got a rod which is welded to some more cable. So electrodes can take any form of these components, or they can be produced from any combination of these components. So it's not just a rod is an electrode. No. The rod and the surrounding conductors around it, they form the electrode, and we commonly call those electrode arrangement. So the purpose of the electrode is primarily to provide an interface. It is an interface between the electrical equipment that it's serving and the geology, the general mass of Earth. In our courses, we cover this. It's quite an abstract concept, but the general mass of Earth is loosely can be thought of as planet Earth, and that can sometimes be mind-blowing. So I like to sort of rein it back a little bit and say it's the interface between the electrical system and the geology around the electrode. But one of the key features that an electrode must be able to do, it's a fundamental requirement, it must be able to leak a current or voltage into that geology. And returning back to a story that I had many years ago, when I saw a lovely designed electrode grid all buried in and installed. And what the installer had done, unfortunately, is install completely in PVC coated insulated conductor. So immediately there's a problem here, because there is no way or no means that that electrode can leak the current or discharge the current that it's intended to discharge. Okay, more examples. Yeah, earth testing, you can be in a mid part of a construction and there'll be lots of conductors being exposed, or if it's an existing system, then stuff goes missing. Basically, these copper can be particularly attractive to thieves. Also, we're testing for poor workmanship, if you like, with building up of contact resistances like this one shown in the top right-hand corner. So the earth test not only tells us whether a new install will perform as predicted, but also whether an existing one is going to perform as it should do. Maybe there's been some bits that have been added or taken away, and you just need to know what's going on. The methods of earth testing. I've noted down a few here. Dead testing. This is particularly common in the lightning and electrical sectors, where you're testing to a known earth, and that's very convenient and quick, and continuity testing as well. That's another one. Clamp meter testing. This is almost like an amp clamp, where you clamp it around the conductor, and through circuit theory it comes back with a magical resistance value. That's extremely convenient because you can test things live. It does have its limitations though, and it's important to understand those. On the larger systems, now we're talking into the transmission level voltages, where you need to dominate in-ground noise, and because of the sheer extent of the test, you've got to up your game in terms of the current signal that you're injecting, and that's heavy current injecting, which is we're not going to cover that today. That'll be for another time. Finally, what we are going to cover today is the most common one, and that is Fowler potential testing. Okay, so let's have a look at the Fowler potential setup. Just very briefly, we've got the electrode under test, and we've got our earth tester. Now, the earth tester, in this case, is a 4-pole tester, so it's got 2 pairs of terminal inputs, one set to deliver a current, and the other set, a pair, to monitor and measure the voltage. So here we've got the first set of leads are attached to the fixed electrode arrangement, which could be anything, could be that single rod, or it could be a complete extensive 100, 200 meter earth grid. And then we traipse out the second pair of leads. And I want to pay particular attention to the C2 current probe. We call it the reference probe. Some people call it auxiliary probe, but I like to call it a reference probe, because this one is also going to be fixed. It's going to be fixed in a certain distance D. And then you've got your floating potential probe. And what the arrows indicate here is that you basically incrementally measure intervals, if you like, going from the reference probe all the way to close to the electrode that you're testing. So what happens is that the tester sends a signal current down the current probes into the geology, and the potential probe, this P2 probe, picks up the voltage and it measures the resistance it measures the decay in voltage and converts it through Ohm's law and gives you the resistance. So that's the principle. So things to consider, and it's one of the main considerations here. The area of electrical influence. You may have heard this term before. What does it mean? Now, I'd like to use the analogy. If you've got a friend that's sitting next to you or a colleague that's sitting next to you, and they're holding let me get this hot poker. They're holding this hot poker. It is white hot. Now, you're not touching that hot poker. He is, or she is. But you will feel the heat that's irradiating from the hot poker. So it has an influence around the air, if you like, a thermal influence around the air that you're picking up, that you're feeling. Now, it's not sort of technically correct, but it's a similar kind of scenario here, is that the electrode under test, it asserts an area of electrical influence into the geology surrounding it. So this is the influence. And the electrically larger the system, the more influence, the hotter the poker, if you like, is. And you'll notice that in this example I've used here, the area of influence, the reference probe is outside the area of this particular electrode. And that's important. It's important because the Earth test, and this is where it gets a little bit abstract, the Earth test is trying to measure the electrode with reference to the general mass of Earth, the planet Earth. So let's go back to this again. So if that probe is inside the area of influence, it's not referencing the general mass of Earth, it's referencing with influence from the electrode itself. And we can see what happens going back to the results. So here's our electrode under test. Here's our distance d. Say, for example, it's 100 meters, just to keep maths simple. And these are kind of 10-meter intervals that we've tested, and these are kind of the results that we're seeing. So when we're right butted up against the electrode, there's virtually no resistance there that we're measuring. But as we go further away from the electrode, remember, let's just do that again. When we start to move away from the electrode with this P2 probe, we're starting to record the measurements. And they climb, and then this is the perfect S-curve, by the way. They should plateau out. And now we're deep, we're just at the right place of the electrical area of influence. And then all of a sudden, the readings the resistance start to shoot upwards as if they're falling off jumping off a cliff. And that indicates that upward tick in the readings is an indicator that you have sufficient distance in your probe, in your lead setup. So when the results come back and you see that there's an uptick like this, you know that you've escaped that area of influence. And that's the idea here. Okay, so yeah, how far do you go? Well, thankfully, our friends at the BS EN's 50522 have done some work themselves and calculated that we need at least 2.5 times the P distance, the auxiliary electrode, and that's the C2 one that what we like to call the reference electrode, the one that's got to escape the area of influence, at least 4 times the maximum extension. So say, for example, our earthing arrangement is 100 meters, yeah, from our maximum distance that we're going to be in line with our leads. You need to take that reference probe at least 400 meters away to stand any chance of escaping the electrical influence of the electrode. So that is how far. It's also important to try and use a frequency that doesn't interfere with the system frequency. So most in Europe, system frequency is 50 hertz. In States and other places at 60. So using sort of a higher frequency is useful. It doesn't have to be terribly high, because then you start to get skewed results. But anyway, as long as it's not the power frequency, all is good. Okay, so that is how far. So what are the common mistakes? Number one, think bigger. That is, see it a lot, especially on, so for example, if you're involved in, as a user sector, again, the lightning protection sector, and you're testing a type B type of arrangement, which is a ring electrode around the building, your standard set of leads that being provided by the manufacturer of the test equipment is probably going to be sort of a 10-meter lead and a 30-meter lead. So when you're testing the ring electrode, just bear in mind that if your building is 50 meters from diagonal, from corner to corner, and you're testing this building, you're going to need to go sort of 200 meters away to get outside the influence of the to get an accurate measure. On larger systems, for power frequency systems, then typically I don't think we've done anything under sort of 600 meters is the norm. Going up to a couple of kilometers is quite common as well. Common mistake number two is not being aware of your surroundings, I think is a nice way of putting it. Testing underneath high voltage overhead lines. Now this is only sort of 11 kV circuit, so it's the influence isn't going to be that much, but it could be enough. If you've got a 400 kV circuit, the impressed voltages that are going to be picked up by your leads, that you're running these leads out to hundreds of meters, if they're in parallel with the overheads, is going to be significant, and your readings are going to be shot to pieces. So bear in mind, be mindful above ground, but also be mindful below ground as well. So there might be some cables underneath, below ground, steel pipes, cast iron pipes, drainage, storm drainage kind of thing, and all these things will influence the readings that you've got. Now, you're pre-planning. If you know where they are, then you can do something about it. You can go tangentially across sort of power cables, maybe to nullify the effects that you might see in the readings. And likewise with the overheads, you can go tangentially so that they don't, mitigates the electrical pickup. So just being mindful. Number three, use the right tool for the job. If you are testing a single rod electrode for a lightning protection system, you can use a very low power unit. It should be fine, but don't expect to be able to use that unit on a substation where you need to have a lot more punch in the signal that you're trying to read. So use the appropriately sized tester for the job that you've got in mind. And signal strength for the tester is key. Clamp meter is another one. We see clamp meters trying to be used where they're not really designed to be used. Clamp meters, you need to understand the limitations of what can be measured. And sometimes, the clamp meters, all they do is test the continuity between a grid. So you're not actually getting an earth reading from them. So understand the limitations of the equipment that you've got. Okay, I'm conscious that time is now ticking on. Summing up, and I hope this has stimulated a few questions. We've covered the reasons why we test earths and do earth testing. We've covered a little bit of the basics in terms of the electrode and its function. Remember, it is designed to provide an interface with the geology. So that interface is what we're measuring when we do an earth test. And the electrode is designed to leak current and voltage. And we covered the test methods, a few test methods available, but we focused in on the forward potential because it is the most reliable and accepted and commonly well-known method. And finally, we covered the common mistakes. Now, there's much more on this topic in our website. So afterwards, we've got a whole category of errors that to avoid on our blog website on the main site. So I'll cover that a bit later. But now let's throw things out to the floor. If you've got any questions, then feel free, put them down in the chat function. And whilst we're doing that, I just want to go back to when it comes down to accuracy of the measurement. And if you're in the area of influence and you haven't escaped it, what you tend to see, and it's something I should have said it originally, but what you tend to see is a slope like this, and then it stops. So if you can imagine, let's go back to the pen, that when you maybe you put your C2 probe somewhere here. So this is your extent of your measurements that you're going to get. And what happens is that you get this slight slope, but there's no uptick. And you're kind of scratching your head thinking, well, there should be a plateau here. And that's another indicator where to show that you haven't escaped the area of influence. And what this means is that if our actual reading of this electrode is here, say for example, I don't know, it's 1 ohm, whatever it is, and the extent of your lead deployment is only measuring this area here, and you pick 61.8% as a figure here, you can see that you're going to write down this figure here, thinking that's the correct resistance value for the earth map. So it's over optimistic, when in actual fact the true reading is this figure, whatever that figure is up here, which is higher. It means that all your touch voltages or your step voltages are going to be skewed. If you take that, it's over optimistic. So I just wanted to, something I missed, sorry, and just going back to it. Okay, let's go to questions. What is the best type of test point for a new substation? Should each electrode have an access pit which gives access for the C1 and P1 probes? It is eminently more convenient to have a designated earth point and to run your leads. And the reason for this is that it's repeatability, because you're going to get contractors that come in first of all and run tests, and you're going to get the results from that, and that's great. But if you choose a different part of the electrode, the geometry is different in the test, so the results are slightly different, or they might be quite a bit different in actual fact, because there might be a different patch of geology that is influencing the overall site. So the bigger the site, the more complex it gets. So having designated test points in an earth pit is a good example, or earth chamber, where you can put an in-pit earth bar sometimes, and have those the leads coming up is a really good idea, because then it forces the subsequent testing engineers to go to the same point. And if there's a drawing record on site which shows where the leads were deployed previously, that's great too, because they can then repeat, providing they're not repeating an error, they can repeat what has gone on before. So then you get a comparison, a true comparison over time of what the earth readings are doing. So yes, I would say put an earth pit in or an earth chamber and make it a designated earth point for testing is a great idea. Otherwise, it introduces an element of variability, which is never good.
But just to add to that, if you're testing the overall resistance of the substation, you only need to do that once. So you don't necessarily need to make every single earth rod have a pit. Only the single one where you intend to connect your test leads to.
That's a very good point.
And so what we sometimes find is that having lots and lots of earth pits everywhere attracts a bit of unwanted attention. So if you weld your earth rods and bury them and just have a single earth pit, that's going to be much less attractive to thieves as well.
Yeah, massively. Okay, what's the opinion of using ground enhancement materials, specifically when the soil is made up of coral? My word. All right. Okay. When the soil's made up of coral, I take it this is not subsea. Enhancement materials, finely granulated bentonite. Bentonite is a form of clay. It comes from Cyprus in large volumes from Cyprus. There are other places, and it absorbs moisture very well. But when it turns into like a slurry and a clay kind of consistency, that fineness of granularity helps that interface connection that we talked about earlier, because of the fineness of the particles that are surrounding the electrode. Let me go back to this slide here. As a way of comparison, have a look at, let's put the latest one, this granularity. Now, I know that this type 1 is going to get covered with more type 1. Now, that, you can see the point contact that's going on here is not really a very good interface with the geology. It's not providing that good all-around contact area that you want to go around the actual conductors. And this is one of the features that ground enhancement material does, because it is so fine. It's like starts off as a powder and then it ends up as being just a super fine material. You get a massive, fills all these voids in, and you just get a really improved interface connection. So hopefully that makes sense. There are other enhancement materials that have an additional feature, which is that they're doped with electrolytes. So they not only improve the connection, the interface, but they dope the mineral content to enable to increase the conductivity, if you like, of the surrounding geology locally. And so in that respect, as long as the minerals are not detrimental to the environment, I think it's a thumbs up for the enhancement materials where they're needed. Normally, if you've got a problem with your earth connection, then use them. Otherwise, if you can use the raw material that came from the excavation in the first place, then you're not actually, you're not having an environmental impact. Long-winded way, but hopefully that covered your question. So yes, I would use them on the difficult rocky situations like this where you've got big voids happening. So the coral, I think it's got properties similar to chalk. That's again another sedimentary. Typically, you're looking at around 350 ohm meters resistivity, apparent resistivity in that kind of range, maybe a little bit higher, up to 400, 500 range. So it's in the medium resistivity range, I'd say. So yes, you might, unless you can get under the coral layer, then the enhancement materials might work well if they've got that doping, because the coral material itself is actually not that granular, or it shouldn't be. Ooh, and the water table. Yeah, testing with water table is an interesting one. And it is, again, it's being mindful about what's going on around you. Coastal installations, particularly that are tidal, you're going to see the tide go every 6 hours or so, go up, down, and water table will likewise go up and down. And you'll see this. You'll see if you did hourly earth tests over, say, a month of period, you will see the cycle go up and down, up and down. So be mindful, especially if you're in areas where there are tides, the seawater particularly, that will have a massive impact on your earth readings. So it can be useful to actually take tests over time. Right, another one. If a test point is to be installed in a dedicated chamber to the substation, can this be cable connected to the buried grid as a radial connection, or should it be a loop connection, or I guess that like a duplex, e.g. a small bar connected at each end? The better scenario here is a loop, so that you've got two connections going back. So you've got current division almost happening. But I don't think it'll make a massive difference to have a radial spur just for the testing, for testing purposes. I can't see that being a problem, because you're electrically connected to the earthing arrangement. It might be better to have two connections, so that if it's the old adage, if one gets severed by a digger or something, or inadvertently ripped out or disconnected, you've got redundancy with the other connection. So hopefully you can see, I've just bounced onto our main site. So this is greymattersglobal.com. If you go to the blog section here, this is a really useful library of reference material that is in bite-sized chunks and easily digestible. So for example, we're looking at earth testing. Just click on the categories here, and you've got 5 pieces that cover earth testing. A lot of the infrastructure these days is decades old. So how do you know it's still performing in the same way that it was in 1950? And is that relevant for 2021? Is it still performing the safety levels that you intend? So there's a whole load of information in this technical blog section here. It's all free to access. There's videos there as well. Really useful reference site. Okay, let's go back to what next? Sustainability. I said it at the beginning, you'll have complete access to the back catalogue, completely free, and all these webinars and previous ones. So that's a nice bit of good news. Okay, as always, there are a number of ways that you can engage with us. Aside from these free webinars, you can level up your technical knowledge at our online academy, and there's Introduction to Earthing, which is like an awareness course, but there are also one-to-one courses where we go into a lot more detail, level 1 and level 2, on earthing fundamentals and electromagnetic fields and things like that. So you can also engage with our design services. You'll be in safe hands. You've got the top 1% minds in the business working on your projects with the top 1% software, using the top 1% of equipment. I had an interesting photo that came up the other day of the equipment in our van, and it is mind-blowing. Anyway, which reminds me about the software, is that we're also the UK and Ireland's support agent for XGS Lab, which is the modelling software that is used in earthing design. And later next month, we've got the launch of XGS Shield, which adds the capability of being able to model the rolling sphere for lightning protection design. So it's something that I've been waiting for about 20 years to actually arrive. And it saves a massive amount of time, and it's a foolproof kind of way of getting your lightning protection design optimized. So that's exciting news that's coming up next month. Okay. I've just mentioned the other resources, our technical blog site that's free to visit. Fill your boots with the stuff that's there. You'll probably get an email after this session with these links to the resources. And I just want to take a moment, as always, to thank Hugh, David, people behind the scenes that help us make this what it is now. So thank you very much for attending this webinar, and I look forward to seeing you not next month. We've got a holiday break next month, August, but it'll be the month after, in September, when we're back again with another webinar to entertain you. Thank you again, and look forward to you next time. Before going completely, there was one last question that didn't manage to get covered during the session, so I'd like to address it here now, which is, what is the life expectancy of bare copper conductors in soil? Which is a great question, and it kind of depends on the acidity and the hostility to the copper from the soil that it's sitting in. So there is no kind of easy answer, but we would typically expect a life cycle of around 50 years. And again, it does kind of depend on the size of the electrode as well. If it's sort of 50 by 6 or 300 square mil, that's a lot of copper, and it's going to take quite a lot of time for that to degrade and corrode and disappear. But again, it does kind of depend on the acidity of the soil. So hopefully that answers your question, and look forward to seeing you next time. Cheers for now.